cordon.
Oh, that is cool.
That is kind of cool. Looks like something George Orwell might have liked. Go into the future, right? All righty, so here's our PowerPoint. And start. All right. Measurements. Now, many of you have probably already taken measurements in some sort of science class. You may have taken measurements at home. If you're remodeling your house, one of my favorite pastimes is home improvement. So in science, we take measurements that are related to what it is you're working on in lab. And in general, there's two giant categories of measurements. There's the objective measurements and the subjective measurements. So those are important terms. Objective versus subjective. What might be the difference between an objective versus a subjective measurement? Any ideas? Yes.
Like a subjective measurement would be like a dash of salt or a pinch of salt.
Say that again.
Like a dash of salt or a pinch of salt, like for a recipe?
It requires the interpretation of the user. So a
Yeah.
pinch might be a little different to me than a pinch to you if you got big pinching fingers, right? Okay. So a subjective interpretation or a subjective measurement requires interpretation by the observer. How green is the grass? This solution had more bubbles than this solution. An objective measure is what we tend to use first in science, which involves generally some kind of a tool. Length, you've used meter sticks or measurement tools like a ruler. Volume, we have graduated cylinders, beakers, flasks, all kinds of good stuff in the chemistry classroom. And mass, you use the balances to measure grams. Those are very objective measures because they require a tool. And generally, because they require a tool to measure them, they're also going to have units associated with them. So that's the big picture of what we're going to be talking about today. So it's a number that generally you're taking using a tool that has a unit attached. And in chemistry, the units are super important because that tells me what the number is. If you say 3.17, is that 3.17 bunny rabbits? No, that's probably 3.17 centimeters or 3.17 grams or something like that. When we make measurements, we have what we call a level of uncertainty, and that relates to two vocabulary words that we haven't talked about yet. This idea of uncertainty is related to precision and accuracy, and we'll talk about that in just a minute. When we're using the metric system to make objective measurements using a tool, our base unit of measurement for length is meter. This is what we call the Systems International, and you'll hear it abbreviated by Corwin, your author, as the SI units. SI stands for Systems International. And we have to have this international system of units because if you measure something here and somebody else measures something in China or Saudi Arabia, we all have to have a common basis for that measurement, and that's why it's the Systems International method of measurement. So meters are base unit for linear distance from one point to another. Gram is mass measurements, and liter is for volume or three-dimensional measurements. So, for example, if we're talking about a candy cane, but before we actually go into how to make these measurements, let's talk about precision versus accuracy really quickly. All right, so I want to make sure that we have these definitions common to all of us. So, that's not showing on the overhead. It's showing on my computer. Well, I'm going to write definitions down here because it's recording on my computer, but I'm going to talk as I'm writing. So the two definitions, the first one is precision, Precision, versus accuracy. I'll figure out how to make it so that you guys can see what's going on this screen. I don't know why that is not working. All right, so precision versus accuracy. In the American vernacular, unfortunately, we use these terms interchangeably often, and that is incorrect. Does anybody have any idea what's the difference between precision versus accuracy?
The accuracy is typically how somebody can describe how precise a person is, either very accurate, not that accurate. Precision is precise on the point.
Well, I don't like to use one word to define the other. How about the differences? The differences. Can you tell me the difference?
I guess if you let's say you're throwing darts in a dartboard, you hit the bullseye, you're accurate, but don't hit the bullseye, but every single one of your darts is around the same spot, that's precision.
Okay, you've been reading the book, haven't you?
I just wrote it.
Because that's the metaphor, the analogy that Corwin likes to make, is the whole bullseye thing. And I've seen that, and it actually does make a lot of good sense. So if we're talking about a bullseye, what's your name?
Ryan.
Ryan said that if you hit the bullseye, then you're accurate. You're actually getting what it is that you want. Or in the case of a measurement, when you measure something, your accuracy is how close your measurement is to the true value. Like if we had some super duper, super good instrument, super precise instrument that we could use that measured down to the tiniest fraction of what something's length was, and then we took our metric ruler in your lab tub and we measured the length of that thing, how close your measurement was to the true or best measurement would be accuracy. So accuracy has to do with how close your measurement is to the, and I'm going to put in quotation marks, true value. And to you, true might mean the best measurement you could possibly make with the most precise measurement tool. All right, so that's accuracy, how close your measurement is to the true value. So how is that different than precision? Let's not use accuracy to describe precision, vice versa.
Well, you can be precise and not accurate
You sure can. How could I be precise and not accurate in the bullseye metaphor here?
by not hitting the bullseye, but hitting the same spot over and over.
There you go. So that was the first dart that was thrown. And then the second guy gets up, right? And he throws. Right? And he's not real accurate, but he's precise. Precision has to do with repeatability of a set of measurements. So precision is repeatability of a set of measurements. All right, so for example, if I gave everybody that candy cane to measure, let me go back to our PowerPoint here. I gave everybody that candy cane on the screen to measure. And we use the first ruler here. I think we'd all agree that it's at least 4 of what, centimeters, here we go. We'd all agree that it's at least 4 centimeters, right? Does anybody not agree that it's at least 4 centimeters? All right, so at this point we have a very high level of repeatability. We have a very high level of precision because everybody agrees it's at least 4, right? The next digit might be a little bit more difficult to determine. We could say it's somewhere between 4 and 5, but without looking at that bottom instrument, if we only had the top tool to measure that candy cane, what might we say that measurement could be?
4 and 4?
Well, we don't like fractions in science, so I'm going to throw you onto the bus right away. We all use decimals in here, no fractions ever. So we can get over that right away. Go ahead.
4.25.
Oh, even better. See, he made that conversion right in his brain. 4.25. I would agree that that probably could be an estimate. However, this brings up an important topic. When you're making measurements, and this is something you should write down, and this is a sort of a subtext of accuracy, when you're making measurements, what you need to make sure is that you measure to the limits of the instrument plus 1 that is estimated. I'm going to say that definition again. When you're measuring anything in lab, and this goes from this point forward into chemistry lab for the next 15 weeks, anytime you use an instrument in chemistry lab to measure something, you must go to the limits of the instrument plus 1 more that you estimate. Well, if we go back to the slide with the candy canes, and we look at that first one, what's the limit of my first instrument here?
4.
Whole numbers, right? 4, 5, 6. All right, so we can have have a high level of precision with that first digit in the whole number's place. So we would all write down 4 point something. The next digit is what we call our digit of uncertainty. And the digit of uncertainty is the one that you have to estimate. Would it be appropriate for me to say 4.2 for that measurement? It would. Would it be appropriate to say 4.3? Yes, it would. It's a little difficult to say 4.25, and I know you said that because you were converting your fraction from a fourth to a decimal equivalent, and that's good, and you didn't know the rule. But now you know the rule, so 4.25 would be 2 digits beyond the precision of that particular instrument. So you can only go 1 beyond. So it would be appropriate to have 4.2 for what you report. 4.3 would be appropriate. 4.25 would not be appropriate, okay? Now if we look at the bottom instrument, ruler B, I can say that ruler B has a higher level of precision than ruler A. It would also measure something with a higher level of accuracy than ruler A. So if I use ruler B and I pass ruler B around to everybody in the whole class, I think we'd all agree that it's at least 4, right? It's at least 4.2, since we don't use fractions in here. All right, so 4.2 now is our digits of certainty. That's what we would all agree. So we would have a very high level of precision in terms of those first 2 digits. The third digit then would be my digit of uncertainty, and that's the one we would have to estimate. What would you guys say it would be, that last digit? 4.25. So now with this particular instrument, it would be appropriate to record that value as 4.25. So now let me show you what I'm talking about here. I'm going to go back to the doc cam. I know you guys can't see this too good, and I don't know why that's not working. Let me try. Okay, well, that's all right. We've got 3 different graduated cylinders here. The first one is a 10 mil graduated cylinder, very small. The second one is a 100 mil graduated cylinder, which is much bigger. And the third one is a 250 graduated cylinder, which is significantly larger than both of the other 2. They each have a different level of precision. Here's what I mean. If you look at the 10 mil graduated cylinder, each of the markings, I'll put this up on the board in just a minute, each of the markings goes up a single digit. So it goes 1, 2, 3, 4, 5. So if we're looking at the graduated cylinder, the 10 mil, each of these markings goes up a single digit. Then in between each of those markings, there's 4 smaller marks. 1, 2, 3, 4. Right? Each of those smaller marks in between the bigger mark must mean how much? What do you suppose they must mean if there's 4 of them? Right? This is 1 and that's 2, so this must be 1.2. This must be 1.4, 1.6, and 1.8. So in that case, 1.2, 1.4, 1.6, 1.8, the limit of my instrument is whole numbers, but it also goes to tenths, right? So I could read that, and for sure we would all agree because those markings. So if we had some liquid that was in between, and I'm going to expand this so you can see it better on the board. Here's the 2, and here's the 1, right? Here's the liquid level. This is where 1 is, and that's 2. If I expand it here, 1 to 2, and then we got 4 marks in between. If the liquid level is between the first and the second mark, what would we record our value of liquid here? I would say it's, what would be the first digit I would report? 1, okay, we all agree on that. What would be the second digit I would report? 0.2. Okay, does anybody disagree that it's not at least 1.2? So far, we have a very high level of precision, right? We have a lot of agreement here. Now, we have to interpret. There's our digit of uncertainty, that last one. So we could say in our liquid level, it's 1.2, maybe 5. Okay. That's the very smallest. So when you have a graduate, you have to measure the volume of something, and you want to measure it as precisely as you can. If the volume of that particular thing is less than 10 mils, then of course your 10 mil graduated cylinder would be the very best thing to use because it has the highest level of precision and accuracy, right? All right, so you look at the next one, the 100 mil graduated cylinder, and now the derivations are divided up into tenths. So what you're going to have is you're going to have 10, 20, 30, 40, 50. Right? And in between, there's smaller derivations. 10, 20, 30, 40. And you have a bigger one, and then you got 1, 2, 3, 4 smaller ones in between. So what's the level of precision with this instrument? I could report, say my liquid is somewhere in this vicinity. Right here. What would be the first digits I would report? 10. Okay. Point. What would be the next one? Right, so each of those must be 1. 1, 2, 3, 4. All right. Does anybody disagree that it's not at least 10.4? We have a very high level of precision because our instrument is fairly precise. So this instrument is precise to tenths. This instrument was precise to tenths. So now we have to estimate one more beyond tenths. In this case, I would estimate to what? 0.45 perhaps? Okay, so millimeters. Finally, we have a really big graduated cylinder. And now, instead of going up in single numbers or in tens, we go up in quantities of 20. So it goes 10, 30, 50, 70, 90. So this has a much lower level of precision. So if we're looking at this particular graduated cylinder, it goes from 10 to 30 to 50 to 70. All right, so put that up here. Now it's 10 to 30 to 50 to 70. If we look at the individual derivations in between, they're the same as this is. Hang on just a sec. Yes, you have a question?
Me?
Yes.
Wouldn't that have been 14.5 milliliters?
Because it was in between 10 and 20.
Did I? Oh, see, I messed up, didn't I? I was listening to what you guys were telling me and not thinking for myself. Let's go back. You're right. Let's go back and fix that. All right. Don't want anybody to be mistaken. All right. And I said it was somewhere in here? Yes. All right. So, yep, 10, 11, 12, 13, 14. How come nobody objected?
I was scared.
Thought I was going to throw you under the bus?
When you said, does everyone agree, I said it in my head, but I didn't say it.
Okay. I was just checking to see if you were listening. Right? Okay, so 14 points, what would this be? Okay, so now, that's our digit of uncertainty, right? I messed up before, so change your notes. That's the digit of uncertainty. So now if we look at the 10 mil graduated cylinder, it's precise to tenths. We have to estimate to hundredths. The 50 mil graduated cylinder is precise to ones, and we have to estimate to tenths place. So if you have less than 10 mils, you want to use that one because that has the highest level of precision. But if you got more than 10 mils and less than 50, you're going to have to use this one. But you give up a little bit of your precision, right? All right, so finally the last one. Instead of 10 and 20, 30, 40, 50, it goes up by 20, so it goes 10, 30, 50, 70. So now we'll make a different number. So this is here, and then we got 1, 2, 3, 4, 1, 2, 3, 4. So if we go, there is where we are. What would I record this volume to be? That must be what here? 20, 30, 40. So if that's 20, each of those little marks must be 2. All right, so there's 30, 2, 4, 6, 8, right? 30, 2, 4, 6, 8. So,
In the middle, so you make it 39.
so see, there's where we have our digit of uncertainty, huh? Because you have to estimate in between. So in this particular instrument, here is our digit of uncertainty, right? Because that's what we're going to have to estimate in between those, so we could say 39, and I think that would be probably the best measurement. You're not going to go to tens place on this one, right? Yes?
If that's the case, then how come for like our smaller beaker,
Graduated cylinder, you mean?
yeah, graduated cylinder, put 1.2 or going up by 2s, so if it was a half, would it have been 1.3?
You're right. So 1.3. So that one would be our digit of uncertainty there too, because of the derivations. Let's try. That's hard to see. Let's take this paper out. This paper I think is easier to look at. And although you guys can't see it on the screen, y'all have it in front of you. This one is really, really good at this particular activity. All right. So if you look at number 1, we've got whole numbers there. So let's look at our reading. What would be our first digit that we report for number 1? 8 for sure. Okay, so then after the 8, what am I going to write?
Like a point.
Point, all right. So now we have our digit of uncertainty, right? We all agree that it's 8, but some people might say it's 8.9, okay. 8.9, could you say it's 8.8? You could. Could you say it's 8.85? No, you cannot. All right, we'll come back to this column, the sig figs column, in a minute. We're going to go down the first column with the reading first. Number 2, now we've got the same measurement, but we have a better instrument, just like the candy cane example. The second reading is going to, the first number for sure will still be 8. What's the second number going to be?
9.
For sure. Everybody agrees it's 9. Now is our digit of uncertainty. So what's that last number? We could say it's 5. Would it be appropriate to say 8.94? You could. Could you say 8.96? You sure could. Could you say 8.961? No, that's too many. All right, well, look at the next one. The first number is between 130 and 140, right? So I'd say it's 130 something. So the first two digits, the hundreds place and the tens place, we would all agree we have a high level of precision. But that last one is where we now have to estimate. So it's 133. Would it be appropriate to say 134? Would it be appropriate to say 132? Yes. Would it be appropriate to say 132.5? No. All right, let's go to the next one. They get a little more difficult as you go on. So it's between 2220 and 2230. So that looks like there's 10 marks in between. So between 2220 and 2230, if there's 10 marks, each of those must be a ones place mark, right? So I think we could all say it's 2225. All right, we'd all agree it's 2225. Point, what would we say after that? 5, okay. Could I put 2225.55? No, that would not. Could I put 2225.6? I could. All right, let's look at the next one. Between 110 and 120. Now there's still 10 derivations, so each one of those must be a single digit or a ones number. So what would my first value I would write down? 114, I would agree, right. It starts with 110, then you add 4 more. So that's 114. I think we all agree it's at least 114, right? So now I'm going to put a decimal there. And what would be my next number I would report? 0.1 would work. 0.2 would be appropriate. Would 0.15 be appropriate? No, that's too precise. Okay, you guys are getting the hang of this. All right, the next one, between 1100 and 1200, and there's not any derivations in between. So I think we can only say, we only can agree that it's at least 1100, right? So now our digit of uncertainty is much different. What could we say after the 1100? You could say 1110. You could. What else could you say? You could say, I like 1120. Could I say 1115? No. Has to only be one digit of uncertainty. And see, this is where they get harder. And that's why I like this sheet, because it gives super good progressive examples. Let's go that one again. So the first one we could say could be 1110. It could be 1120. It could be 1130. But could it be 1125? No. All right, let's go on to the next example. Now it gets hard because we're reporting numbers less than 1. Whenever you report a number less than 1, you must write the 0 first and then a decimal in this class. So you must write the 0 first and then the decimal before you write any other numbers, because in science, that's how we show a number is less than 1, and it is essential that you report that 0. So it's 0 point, what would be the next digit I would report?
0.06.
It's another 0, right? Because the first digit that has a measurement is 0.1, so it's less than 0.1, so we got to put another 0 there, right? All right. And now how many little hash marks are there between the 0 and the 0.1? 6. So I think our next digit we would report would be 6. So far we have 0.06. Could I estimate one more number beyond that?
Yeah.
I could. What number should I probably report? 5. Could I put 0.064? I could. Could I put 0.066? I sure could. Could I put 0.0651? No. All right, last one is the hardest one. First number's less than 1, so I got to report the 0. Put the decimal. What would be the next digit I would report? Another 0. All right. Then the next digit I would report is a 2. And I'm counting how many after that 2? 6. Now we have to show that it's right on the money, because our job is to use the limits of the instrument plus 1 that we estimate. If we say it's right on the money, what number would I report after the 6? 0. And that is now our digit of uncertainty that we're estimating based on the interpretation of the observer. All right? And science is pretty fussy about our measurements, you know. We're going to talk about a topic now that we call, and we'll keep this out because we're going to add something to this worksheet after we introduce this topic. And the topic we're going to talk about now is significant figures, or significant numbers. So somewhere in your notes, add a heading of significant figures or significant numbers. Now you go, all right, significant figures. What the heck is a significant figure? I think one of the better significant figures is a lady that just turned 50, I heard, is J-Lo. She looks good. I'll tell you what, that is a very significant figure she's got. That's not the kind of significant figure we're talking about in here. We're talking about numbers. And the only people that care about significant figures in science are the chemists. Okay? The geologists, their numbers are so huge, 60 million years, there's no significant digits in there, right? Biologists, they don't even use math, so they don't count. Physicists, they go into the lab, they measure something, they go, round to 10, so you're good to go, right? Physics. Chemists are the only ones that are fussy about sig figs. So if you go, after you learn sig figs in here, and you go to your physics teacher, and you're reporting some numbers, and you go, oh no, how do you want us to report sig figs? Your physics teacher's going to look at you and go, you just got out of chemistry, didn't you? All right, so what numbers are considered significant? With the numbers that we measure and then our digits that we report are the ones that are significant. So there's some rules to sig figs that we all have to know. Rule number 1, and write this down. All digits 1 through 9 inclusive are significant. So, I used to teach algebra years ago when I was just a high school teacher. So the set of numbers, right, in algebra, 1, 2, 3, 4, 5, 6, 7, 8, 9, inclusive, are all considered significant digits. That's the easy part. Whole numbers are easy to interpret. It's the zeros that start to get fussy. All right, rule number 2. Leading zeros are never significant. Example, leading zeros, numbers that you reported on your sheets would be a good one to look at. The last 2 entries, 0.065, the 2 leading zeros, they are not significant, they are simply placeholders. They were not measured. There was nothing in that place. They are simply placeholders. So 0.065, those two zeros are not significant. 0.0260, the first two zeros are also not significant. So leading zeros are never significant. That's generally because they are placeholders. Rule number 3, I like to boil this down to the simplest rules. Rule number 3, trailing zeros are only significant if, I'm going to use the calculus if. You guys know what the calculus if is? My younger brother was a brilliant engineer, and I was in grad school and he was an undergrad. We came home for Christmas and he was writing a paper and he said, "Lorelei, how you spell if?" I had no idea why he did not know how to spell if, because he just came out of calculus. This kind of if. Anybody seen this kind of if before? Calculus? What does that mean in calculus? If and only if. Right on. So, if and only if. The only way that trailing zeros are significant, if and only if a decimal is stated in the number. For example, good example would be if you look at the third to last measurement, the 1120. Okay, the 1120. That's a trailing zero, right? It's a zero at the end of a number. Is that zero considered significant based on the rules I just told you? No. So what I do is I put a little sad face. And I know it's kind of juvenile, and keep in mind, I used to teach junior high and high school. But it does help students remember. I have students in grad school come back and go, "I still put happy faces and sad faces in my zeros." All right, so that's a good example. Here's another trailing zero that is even a more complex example. The number, I think we had 0.0260, right? These are leading zeros, so are they significant or not significant? Not. So they're unhappy faces, right? Because they're just placeholders. This is a trailing zero. Now we have to decide if he's significant or not. Is he significant based on that rule?
Yes.
Yes, he is. Why is he significant?
The decimal.
Because there's a decimal, so, oh man, haha, I'm significant and you're not, right? We could take a number in geology, right? 60 million years. I think that's about when the dinosaurs were. Anybody seen the new Jurassic Park movie?
Yeah.
Ooh, that was so good. I love sci-fi. I think that was my favorite one of all the Jurassic Park ones. Especially when the surfers surfing. I won't tell you that. All right. All of those zeros are trailing zeros. Are they significant or not?
No.
They're not. So right now, they'd all be super unhappy, a whole row of unhappy zeros. But then all of a sudden, I add that decimal, what happens to them? They turn their frowny face upside down. And now they're all significant zeros. And that's because it implies that it's exactly 60 million years. Not 59,999 years, not 60,001 year, exactly 60,000 years. So that's the difference in science with leading versus trailing zeros. All right, so we got 3 rules. First of all numbers 1 through 9 are inclusive, are significant. Hang on just a sec. Leading zeros are never significant. Trailing zeros are the ones that are tricky because you have to decide if there's a decimal. And the last rule I want you to write down is trapped, T-R-A-P-P-E-D, trapped zeros are significant. Do we have any trapped zeros in here in our measurements? No, we don't. Let me give you a good example of a trapped zero. The year that we are in, 2018. Is the 2 significant? You betcha. Is the 1 significant?
Yes.
Yep. Rule number 1. What about the 8? Yep. Since that 0 is trapped, he's significant too. Yes?
So if that was 60 million and 1 years, then would that be all those numbers was significant?
Because now all those are trapped zeros. Because that's significant, so every 0 in between is also significant. Yes?
If that one was still a zero, would you have to put a zero after the decimal to make it?
Not unless you were trying to state that it was exactly 60 million and some tenth of a year. Like if you instead of 60 million point two, that's 60 million and point two of a year, which is what, like a month and a half or something? 60 million point zero means it's exactly 60 million years, not 60 million years and 1 day,
So all those zeros would be 60,
if the decimal's there.
including the one after the decimal?
If you have another digit here, if it's a zero, is that what you're asking?
Yeah.
Absolutely. Good question. Trailing zeros are still in that rule that if there's a decimal, they're all significant. So if that's significant and that's significant because of that, then all the zeros in between are also significant. Good question. All right. So now, let's go back to this sheet and decide how many sig figs each of these has, because this is super important for the lab that you guys are doing next week. All right, the first measurement, 8.9. How many sig figs is that? 2. Write that down. 8.95. How many sig figs? 3. 133 has 3. 2,225.5 has 5. 114.1 has 4. Okay, now we got to slow down. 1,120 has 3. 0.065 has 2. And 0.0260 has, oh, you guys are so good. This is going to be an easy semester. Easy peasy. All right. Well, you got to look at it for a while, and you may want to go. There's a website I gave no, I didn't give that to you guys. That was my online class. All right, now let's talk about, let's see here. Sig figs. Sig figs in calculation. So next heading on your notes, sig figs in calculations. Let's see here where we can go with this one. Don't know why it's not showing on here. There it goes. Okay. All right, well, let's talk more about, before we go on to that, I want to do sig figs and calculations. So you should have somewhere in your notes sig figs and calculations, and we're going to talk about the rules. There's 2 sets of rules, one for multiply and divide, and one for add and subtract. So what you should put on your paper is 2 headings right now. Sig figs. You're going to have multiply and divide and add and subtract. All right, so 2 headings. Multiply and divide and subtract. 2 different sets of rules. Well, sig figs and measurements, here's the overriding rule. So write this at the top. So sig figs in calculations, here's the heading, sig figs in calculations. Here's the overriding rule. The answer, write this down as I say it, the answer to a calculation can never be more precise than any of the original measurements. So there's the definition I want you to make sure you have. Sig figs and calculations. The overriding rule is that your answer to a calculation can never be more precise than any of the original measurements. That's the overriding rule. So we have a set of rules for multiply and divide, and a different set of rules for add and subtract. But the reason we do this is because the answer to a calculation can never be more precise than any of the original measurements. All right, so say, for example, multiply and divide. If I wanted to measure the density, and that's something I think you actually have to do in the first lab, of an irregularly shaped object, say I have a hunk of gold, or something that I think is gold, and I want to see if it's in fact actually gold. So I want to determine the density of this thing. So what's the formula for density? Those of you that have thought about this stuff before. Any ideas? What's the formula for density? How do I calculate the density of something? Mass over volume, which which is kind of timely because here on the overhead, we're talking about mass measurements, right? Mass measurements you make with a balance beam or an electronic balance, and you guys have done that in the lab. And so say I take my hunk of gold and I put it on one of the balances in the lab that some of you have learned how to use already, and I find out the mass of gold is 17.958 grams. Write that down, 17.958 grams is the mass of my hunk of gold. How many sig figs are in that number? 5. Okay, so keep that in mind. Maybe just put off to the left or the right that there's 5 sig figs in that particular number. So that's easy to do because the mass measurements are easy to make. Now we have to take and determine the volume of that thing, and it's an irregularly shaped object. So using a graduated cylinder, I can do that, and in fact, you're going to do that in lab. How would I do that using a graduated cylinder if I want to figure out the volume of my hunk of gold?
You put water in there, you measure the water, and then you put the gold in there, and how much the water rises is how much it is.
Okay, so if you didn't hear, young lady up front, you got a graduated cylinder, you put some water in the graduated cylinder. Say the first measurement, write this down, we decided it was 12.7 milliliters of water that we started with in the graduated cylinder before we put the gold in. So 12.7 milliliters. I drop my hunk of gold in. The water level goes up to 14.2 milliliters. So it started at 12.7, it went up to 14.2. How could I figure out the volume of my hunk of gold?
14.2 minus 12.7.
Right, so let's see, what is that? 14.2 minus 12.7. Looks like about 1.5. 1.5 milliliters is the volume of my hunk of gold. So if I'm using the density formula, I'm going to take my 17.958 grams and I'm going to divide it by the 1.5 milliliters. All right, now we've got 2 levels of significant figures. The first number on the top, my mass, is 17.958 grams. That has how many sig figs? The bottom number, 1.5 milliliters, has how many sig figs? 2. So in multiply and divide, you count the number of digits that are significant and you report to the lowest value. Write this down. You count the number of digits that are significant and you report the fewest number. So count the number of sig figs and report the lowest. So if I got 5 sig figs in my numerator, 2 sig figs in my denominator, does anybody have a calculator and can calculate this number for me? What's the answer?
You want the...
Give me everything that tells me on the calculator.
So the first answer was 1.1972 E1. That's all I did.
I think with that E1, I think that's 1.19 times 10 to the first.
And then it sig figs it to 1.2.
Well, right. Does your calculator do sig figs for you?
Yeah.
Well, we're going to have to not let you use that on the exam, huh? I'm teasing you. All right, so if we report, if we did the division, and we say 17.958 divided by 1.5 is, I think it's actually 11.9, isn't it? Oh, okay, so let's say 11.972. How many digits does that number have that are considered significant? 5. That's way too many, right? How many do I need to report that to? 2. So what would I round that number to? 12. So I would report 12. And what are the units that I would report? Grams over milliliters. That's what we call a derived unit. A derived unit is something you cannot measure directly, that you must do a calculation or multiple measurements and then a calculation in order to determine. This is a derived unit. Density is a derived unit. Grams per mil. We don't have a densitometer that you can stick in something and it says, oh, it's 12 grams per mil, right? You got to measure the mass of it. You got to determine the volume of it. Then you divide. That's why it's called a derived unit. Right? So you measured 2 units directly, mass and volume, and then you derived the answer as well as the unit. Okay, so that's 2 sig figs. Now, add and subtract. Let's try a different one. Say instead of using the same, well, let's see. Let's try length measurements, all right? So I wanted to measure the length of this room, and I have a big giant meter stick, not up there, and a little tiny, small ruler. And so I take the big meter stick and I measure the long distance of the room, and I find that it's 12 meters. I'm just making up that number, and it's 12 meters. But then I have to take my little ruler, and I'm going to add some numbers to that because my big ruler doesn't have any divisions on it. It only has like one big chunk of a ruler, right? So I have 12 meters, and I measure with my little ruler, and I say, okay, well, that's an additional 0.75 meters. So now what I'm adding up is 12 plus 0.75. So now what you have to do is you have to determine which one of those values was the least precise measurement. Which one of those is the least precise measurement? 12 is the least precise because it only goes to what digit? Ones place, all right? So what I'm going to do is I'm going to add up the numbers just like I normally would. Use your calculator, you can use your head. So if I add the numbers like I normally would, it would be 12.75, right? But because the 2 is my least precise number, when I go through and I have to round the answer to report my answer, what do I have to round it to? 13. Because my answer can never be more precise than any of the original measurements, all right? One of your first homework assignments, you have to determine how many sig figs are in a particular value. So this is where you would go and the rules that you're going to consult as you're going through this. Additionally, any calculation you do in this class, whether it's lecture or lab, from here on out will involve sig figs, okay? So on the quiz or the exam, don't raise your hand and say, are we supposed to round that to sig figs? Because what's the answer going to be?
Yes.
Of course. Always, always, always. And that's why we do this the very first lesson. Okay, so there you are. And you know what? Don't be like me. When I was in your shoes as an undergraduate, what happened to me was the fact that I didn't pay attention to the lecture on sig figs. And what that caused to happen for me was the fact that I didn't understand sig figs the whole rest of the semester. And I kept getting these little dinky points taken off on my lab reports. 2 points here and 3 points there and a couple of points down the line further. And all of a sudden you're going from an A lab report to a B or a C. And so that plagued me my entire first year of undergraduate chemistry work until I finally figured it out because a grad student who was our lab tech was nice enough to sit down and talk to me and tell me the rules of sig figs and explain why they happen. So don't let this happen to you. All right, so if we go down, whoopsie, I'm trying to get back to my PowerPoint here and it's not cooperating, so let me try something. Huh, all right, that's interesting. Let's try. See, it's not showing, Sometimes beginning of the semester, these little things plague you. All right. Let's try this again. That is not cooperating. Alrighty then. Well, now I can't get anything to work. Well then, I guess we will just work through it. I'm going to shut off the recording. We'll have to finish this at some other time because it's not cooperating. And, uh-oh. That's probably what it is. I think this connection is not good. All right, we'll just work.